In this lesson, we'll talk about truth tables and their applications. First off, a statement is simply a sentence that you can establish whether the sentence is true or false. It can't be both, it can't be neither, it must clearly be able to be said this sentence is true or this sentence is false. Often when we work with statements, we'll reference them as statement variables, such as P and Q. And then from these statement variables, we can begin to look at truth tables. Truth tables take complicated logical expressions made from statement variables and break them down to establish the possibilities of when they are true or false. There are 6 basic logical operations that we'll use in this particular video. We have negation, which is usually given by this symbol, the AND symbol, the OR symbol, the implies symbol, which is often read if P then Q, the exclusive OR symbol, and the double implication symbol, often read as if and only if. And we'll go through each one and define it with their truth table. The negation operation is defined similarly to how it sounds. It does the negative, the opposite, if you will, of what the logic currently is saying. So if the original statement is true, the negation will define to be false. And if the original statement is false, we'll define the negation to be true. The AND operation does also about what it sounds like. If you've got 2 true statements, and you take the AND of the 2, that statement is still true. But if you try to claim that 2 things are true with the and you get one of them false, that makes it false. So true and false together make a false statement. Similarly, false and true, as well as false and false, are also false overall. You need 2 truths to make the AND statement true, and you need only 1 or more false to make the AND statement false. The OR statement is true as long as you have at least 1. It's the idea of P or Q, or possibly both. This is not the exclusive OR that we'll talk about in a minute. The OR operation simply says as long as at least 1 is true, the overall statement is true. So if we have true or true, we get true. True or false, we have at least 1 true. False or true, we have at least 1 true. And if both are false, that's when the OR becomes false. Now the implies operation. These are the statements if P, then Q. So if we make a statement and the starting premise is true, and then the conclusion is true, we made a true statement. But if the starting premise was true but the conclusion didn't happen, that would mean that the if-then statement was false. However, what if the premise is false? Well, if the premise is false, there's not much that we can say about the statement. It's sort of vacuous, if you will. And so if the premise is false, we actually assume that the if-then statement is true. Next is the exclusive OR. Like the OR statement, the exclusive OR is true when one or the other is true. However, the exclusive OR requires that exactly one of these is true. If you have both true, the exclusive OR is actually defined to be false. Then, if you have one of these being true, you get true. Again, one of them is true, so you get true. And here you don't have at least one of them true, so it's false, just like the original one. And then the double implication, the if and only if, sometimes called the biconditional expression. This is defined as having both P implies Q and Q implies P. So what we'll do is we'll look at both of them and see what it looks like. True implies true was true, and then true implies true the other way is also true. So we have truth here. True implies false we said was false, so that's enough to say this one is false. False implies true, we said, well, that was true as long as it started with false, but at the other direction, true implies false is false, so I don't have both. Finally, the false implies false. You've got true because it's starting with the premise of false, we just assume it's true. False implies false is true, and then the other direction we also have false implies false, which is also true. One of the things about this double implication here is it's true whenever the two statements have the same truth value. Both true or both false makes the double implication true. Now let's look at the order of operations on these. The order of operations, just like with numbers, we start with parentheses. But then after that, negation is the next one that we look at. And then we have the and, or, and exclusive or that we'll treat left to right as our next level of order of operations. And then the implication as well as the double implication come at the very end for our order of operations. And the reason we do these is so that we can do truth tables and do them in some sort of logical order. Now let's do some truth tables. The negation of P or Q. What we're going to be doing is looking at the order of operations and slowly working our way forward one operation at a time. What I just said was that the negation operation was the first operation to pay attention to other than parentheses. I'm going to look exclusively at the negation of P first. P is true, true, false, false. And the way that I set up this truth table is you notice I've got all four possibilities of when P and Q could be true or false. So if P is true, the negation of P is false. Again, P is true, so the negation of P is false. When P is false, the negation of P is true, and the last one is true also. That takes care of the negation operation. Now we can do the OR operation. We're going to take the negation of P or Q. Now, one thing to pay attention to in general is when you're doing truth tables, you never have to look at more than two columns at a time. If you try to do more than two columns, you may mess yourself up by doing too many steps at once. All I'm doing in this column is the OR, just the OR. I'm taking the OR between the negation of P, which was shown in this column, and then we're taking the OR with Q, which is this column. All I'm going to do is OR these two columns together. True or false is true. False or false is false. True or true is true. And false or true is true. Remember, for an OR, as long as at least one of them is true, the overall expression is true. Next example. Again, by the order of operations, we need to do the AND first, because AND comes before implies. We'll start with Q and R. Remember, with an AND, it's true only when both are true. True and true is the first one. That's true. True and false is false. You don't have both. False and true is false. False and false is false. And then similarly we get true, false, false, false. Now we do the implies part. We're going to do P implies, and I'll use parentheses here, Q and R. What we're doing is looking at P implies Q and R. I'm looking at this column and this column. Now remember your truth table for implies. True implies true is true. True implies false is false. But if we start with false, we immediately assume that the statement is true because we really can't tell otherwise. True implies true is true. True implies false is false. True implies false is false. True implies false is false. And then for the rest of it, you'll notice we're all starting with false. So regardless of what these values are, I'm going to get true for all of these. Here's one of the applications of truth tables. We say that two statement forms are logically equivalent if when you compute their truth tables you get the same values of true and false for the same cases. Basically, if you compute their truth tables, you can look at the final columns and say those are the same. If they don't match up in some way, then they are not logically equivalent. Another definition of logically equivalent is that if you form the if and only if between the two statements, the if and only if will come out true in every single case. Let's do this example. To do a truth table to show two things are logically equivalent, What you usually do is separate the truth tables into the left side and the right side. For the left side, notice I have a set of parentheses. I'll say P implies Q will get me started. Just like on the last slide, true implies true is true. True implies false is false. False implies true, we assume to be true, as well as false implies false. Next we'll do the negation. The negation of P implies Q will just simply be the negation of this column. True becomes false, false becomes true, true becomes false, and again true becomes false. Now that finishes the left side of this statement. What I'll do is I'll draw a double bar to represent that I'm done with the left side. Then let's move on to the other side. Again, negation is the first operation compared to ands and ors, so I'm going to do the negation of Q first. The negation of Q means I'll look at the Q column here. True becomes false, false becomes true, and so on. And then I'll do the AND operation of P and the negation of Q. Here's your negation of Q column. Here's your P column, and we'll AND them together, meaning it will be true as long as both are true. True and false is false. True and true is true. False and false is false. And false and true is also false. What we do from here is we look at the last column of the truth tables. Notice that the last column of each part are exactly the same. That's all we'll say here. They're the same, so they're logically equivalent. Next example is one for a not equivalent, and this is a truth table with 3 variables. What this particular equivalence is saying is that if you have an OR with an AND, you are not allowed to just move the parentheses and do them in a different order. We're going to find that we get a different answer in that case. Let's go through both sides as usual. We'll do the parentheses first, which is Q and R. True and true is true. True and false is false. False and true is false. False and false is false. And the rest is exactly the same because it repeats. Now we'll do P or Q and R. Again, the OR operation is true as long as at least one of them is true. True or true. True. True or false. True. And you'll notice since P is true, I can just say it's true all the way down to here. False or true. True. False or false. False. And the rest are also both falses, so we get false for the last 3. That's the left side. Now on the right side, we'll do the parentheses first, the P or Q. Again, for an OR, it's true as long as at least one is true. So for P or Q, the first 4 will immediately be true because P is true. Then for Q, we have false or true is true, false or true is true, and the last 2 are both false. Finally, let's do the AND operation. We've got P or Q and R. So I'm looking at P or Q as a column and R as a column, and I'm going to AND those 2 columns together. True and true is true. False and true is false. We need both. True and true is true. False and true is false. True and true is true. False and true is false. These last 2 are false, so the AND is false. Here's the verdict. If I look at the last 2 columns, I find some discrepancies. Notice that everything else is the same except for these 2 positions. They are different, so this is not logically equivalent. There's a few other logical equivalences that I have here for you to try. Feel free to pause this video if you want to take a look and try them out, but you'll find that every one of these logical equivalences hold as I have written. But what's interesting here is that if I have just the negation and the AND operation, I can actually define all the other ones in terms of just negation and AND. I can start out by defining OR as the negation of P and negation of Q. And then once I've got the OR definition, I can go with P implies Q to be from negation of P or Q. Then the exclusive OR can be P or Q and the negation of the AND. This basically takes out the possibility of both being true. And then finally, P if and only if Q, I already told you, was both P implies Q and Q implies P. Two more logical equivalences come from some of the statements that you can make from a general conditional statement. The converse happens when you switch the order of the statement, and the contrapositive happens when you switch the order and negate. It turns out if you switch the order, it is not logically equivalent. But if you switch the order and negate, it is logically equivalent. These are some interesting things that you might want to try. Here's the last application of truth tables. What we have here is what we call an argument. An argument is basically some premises that we're assuming to be true, potentially, and then some sort of conclusion that we make from them. When we state a conclusion, we often use the symbol therefore, which is drawn as 3 dots. And the idea is we want to know if these arguments are valid, if they make sense to say. The first thing that we often do with these is we'll rewrite them with statement variables. If triangles T1 and T2 are congruent, we'll call that part P. Triangles T1 and T2 are congruent. Then T1 and T2 are similar. We'll call that Q. This first statement is P implies Q. Triangles T1 and T2 are congruent. That's just P. Therefore, triangles T1 and T2 are similar. That's just Q. We're asserting that if we have P implies Q and we also have P, then we get Q. Let's do another one. If a quadrilateral Q is a rectangle, we'll call that P. Then both pairs of opposite sides of Q are parallel. We'll call that Q. This gives us P implies Q. The quadrilateral Q is not a rectangle. That's the negation of P. Therefore, Q has a pair of non-parallel sides. That's the negation of Q. We have two forms of arguments made with statement variables, and what we're going to want to do with these is figure out if they're valid. What does it mean for an argument to be valid? It means that the conclusion is true every time all of the premises are true. If you ever have all the premises being true but the conclusion is false, then we get an invalid argument. We'll just go through all the cases and figure out where the premises are true. To do these, we'll start by making our truth table of the premises. We'll do P implies Q, and then I'm going to go ahead and copy P into my truth table. Usually I put a double bar here as well. P implies Q. True implies true is true. True implies false is false, and the other two implications are both true. Then I'll copy P, true, true, false, false, and these are my two premises. There's only one place where both of my premises are true. Right here. What I'm going to do is go to my conclusion Q, but I'm only interested in writing it down when the premises are true. In this particular row, we have both premises true, and you'll notice that Q is true. That satisfies the definition of valid. This is valid since the conclusion is true when all the premises are true. Let's do the second example. Again, the first thing that we'll do is we'll take our premises, P implies Q, as well as the negation of P, and we'll look at when those are all true to get us started. P implies Q is again true, false, true, true, just like in the last example, and then the negation of P is false, false, true, true. This time we have two rows that have all the premises being true. What we'll look at is the negation of Q as my conclusion, but again, I'm only interested in writing it whenever the premises are true. Here, Q is true, so the negation of Q is false, and then Q is false, so the negation of Q is true. This is the problem. I have one row where the premises are true, but the conclusion is false. That means that this is invalid. Invalid since a possible conclusion is false when the premises are all true. Here's one final example. If 4 is greater than 0, then 4 cubed is greater than 0. And then we have 4 cubed is greater than 0, therefore 4 is greater than 0. The question is whether the argument is valid. With something true listed here, you might consider it immediately. Sure, 4 is greater than 0. But let's look at this a little bit closer. If we change this over, we can say this is P implies Q. And then we're given Q. And then we'll say, therefore, P is what we have. And we want to know, is this a valid argument? Let's start with our premises. P implies Q, and I'll copy Q to make this easier. P implies Q is again true, false, true, true here. And copying Q, I get true, false, true, false. I'm interested in the places where this is all true. And then we'll look at the conclusion of P in those locations. In this row, P is true. In this row, P is false. Therefore, the argument is invalid. And we'll keep the reason out since we wrote it on the last slide. Now let me point out what's strange about this. This conclusion was a true statement. 4 is greater than 0. However, 4 being greater than 0 did not follow from this statement being true.